Hello students, welcome to my YouTube channel Data Shah. In today's lecture, we'll be talking about the unbounded solutions of the linear programming problem, how we could find out that whether we are getting an unbounded solution. So in simplex method, unbounded solution occurs when there is an entering variable but there is no leaving variable found. So there are two cases where for the leaving variable we have to consider the minimum ratio. So if in the minimum ratio we are getting the negatives, all of the minimum ratios are in negatives, then we can say that it's an unbounded solution. Second case, when it becomes infinity, that means when we are dividing the basic solution with the coefficients of the AIs, then in that case, if it is 0 in some denominator, it becomes infinity. So that also can be considered as the unbounded solution. So let us consider this example where we are having maximize z is equal to 5x1 plus 4x2. x1 is less than equals to 7 and x1 minus x2 is less than equals to 8. So as we could see, again this is a less than equal to type and we have to add the slack variables. So if we'll be plotting our equations here, the constraints, so we could easily identify that this is suppose x1, x2. So x1 is equal to 7, we are talking about this, and let me just take this as x1 minus x2 equal to 8, right? So this is my line, this is minus 8 plus 8, this is plus 7. So now the region that we have to identify here would be this is less than equals to 7, so obviously this, and this is also less than equals to 7, the line, so this would be this only. So what's the common area? So the common area that you could find is this. Even if we are saying that x1 is would be remaining 7 only, but we can't tell anything about x2 and we have to find out the maximize z. So according to the objective function, we are getting an unbounded solution here. So graphically we could find out and examine that this is an unbounded solution, but how would we could identify using the simplex method? Let's consider. So here I can write my linear programming problem in the standard form as maximize z 5x1 plus 4x2 subject to the constraint. So x1 this is 0x2 plus s1 equal to 7, so and then x1 minus x2 plus s2 is equal to 8 with the 0 cost. So I can also write it here like this, where x1, x2, s1, s2 are all greater than equal to 0. So as we could see, the first initial table that we are getting here is Cj, we have written 5400. The basic solution that we are getting is s1 as 7 and s2 as 8. This is their cost, so z is coming out to be 0. So I have plotted all their coefficients here. So we could easily identify zj, it's coming out to be 0 because 0 multiplied by 1 plus 0 multiplied by 1. So everything is 0 because here cb is 0. Delta j would be minus 5 minus 4. So this is our entering variable, and the leaving variable we could identify 7 upon 1 and 8 upon 1. So this would be our leaving variable because that's the minimum. So this becomes my pivot element. So in the next table that we'll be creating, so s1 would be leaving the basis and x1 will be entering the basis. So that's the same, entering, this is the leaving, and this is the pivot element. As it is already 1, so we don't have to do anything here. So I'll just enter x1, the coefficient is 5 7 1 0 1 0, and s2 I have to just subtract them and nothing else has to be done. minus 1 minus 1 1 1, coefficient is 0. So here z is now coming out to be 35 and zj is 5 0 5 0, and delta j, zj minus cj, is coming out to be minus 4. This is 5 minus 0, 0 minus 0. So what will you notice here, that in this case, when I'll be finding out this is the most negative, so that means this is the entering variable, right? So x2 will enter the basis. Now what will be the leaving variable? How we could identify? Here I am having negative, that means 1 upon minus 1 would be giving me minus 1. So I told you, if the minimum ratio is negative, so we'll not be considering that part. We always do this in the simplex method. Also here I am having 0, that means if I take 7 divided by 0, 0 is in the denominator, it becomes infinity. So we cannot consider here the minimum ratio. So that means from this table we could find out that x2 is the entering variable, but we are unable to find the leaving variable. The reason I have given you, because the coefficients of x2 is 0 and minus 1, but we have to consider only the greater than 0 positive ones. So thus the solution is unbounded. So we are getting an unbounded solution. So let's consider one more example here. In this we have maximize z is equal to 2x1 plus x2. x1 minus x2 is less than equals to 10, and 2x1 minus x2 is less than equals to 40. Again, if you will plot it graphically, again you will get unbounded solution. So let me write the LPP in the standard form first of all quickly. So maximize z, 2x1 plus x2 plus 0s1 plus 0s2 subject to the constraints. Where x1, x2, s1, s2 are all greater than equal to 0. Second step, we have to find out the basic solution. s1 is 10, s2 is 40. So the initial table that we'll be getting here, so this is the same process as the simplex method. Now zj is coming out to be 0 and delta j is minus 2, minus 1 and 0, 0. So this is the most negative, and we could identify the minimum ratio is 10 and 20. So this becomes the leaving variable, right? So when we'll be making the first table, this was the initial table, and this is the leaving variable. So the pivot element that we have is this. So as it is already 1, so s1 would leave and x1 will enter the basis. So x1 has the coefficient 2, 0. So there is no change in the row 1. So I'll write it as it is. Row 2 would be row 2 minus twice of row 1. So using this elementary row operation, I can make it 0. So 40 minus 20 is 20. So minus 1 plus 2 is 1. 0 minus 2, and this is 1. So z is now 20. Zj is 2 minus 2 to 0. Delta j is 0. Minus 2 minus 1 to 0. So what we could see here, again I am this would be the entering variable, and the leaving variable we have to decide. As this is negative, so we'll not be considering this. This would be 10 upon minus 1, that is minus 10. So I'll not consider this one. I'll be just considering this 20 upon 1, which is 20. So this would be my leaving variable. So this becomes my pivot element, and as it is already 1, so x2 will enter the basis, and the row 2 would remain as it is, and row 1 I'll just add them so that I can make it 0. So 10 plus 20 is 30, 1 minus 2 is minus 1, and 0 plus 1 is 1. So z is now 60 plus 20, 60 plus 20 is 80, and zj is coming out to be 2, this is 1, minus 2 minus 2, this is 2 plus 1, 3, delta j is coming out to be 2 minus 2 0, 1 minus 1 0, minus 4, and this is 3. So according to the process, minus 4 is the most negative, but here you will notice that these two are again negative, right? The coefficients of S1 are negative in this column. So if I find out the minimum ratio, this would be 30 upon minus 1, that's minus 30, and this is 20 upon minus 2, that's minus 10. So both are negative. So I'll not be considering these two. So as both are negative, so we will have an unbounded solution. So again, entering variable is there, we could find the entering variable, but for finding the leaving variable we are facing an issue again in the minimum ratio, so it becomes an unbounded solution.